The machine was finished before anyone knew how to make it think. 18,000 vacuum tubes, 40 panels, 30 tons of wiring stretched across a room at the University of Pennsylvania, and not a single line of code existed to run through it. The engineers who built it understood the hardware down to the last resistor. Not one of them knew how to program it, because in 1945, that discipline did not exist yet. It would be invented from nothing by 6 women the United States Army had classified as clerical staff. This is the story of the ENIAC programmers, the women who turned a room-sized calculating machine into the first true general-purpose computer, doing it without a programming language, without documentation, and in several cases without the security clearance to even look at the machine's wiring diagrams for the first weeks of the job. Before there was ENIAC, there was a job title the United States Army used constantly during the war and almost never explained to the public. Computer, not a machine. A woman. Hundreds of women, mostly with mathematics degrees, worked at the Moore School of Electrical Engineering, calculating artillery, firing tables by hand, the precise trajectory data that told gun crews how to adjust for range, wind, and altitude before ever pulling a trigger. Each table required thousands of individual trajectory calculations worked out with mechanical desk calculators and sheer arithmetic endurance, and even skilled human computers took weeks to complete a single table that artillery units needed constantly and immediately. The math was not simple. It involved solving differential equations that described a shell's flight through changing air resistance, and doing it by hand over and over for every combination of gun, shell, and weather condition the war produced. The Army's solution was to build a machine that could do the calculation electronically in seconds instead of weeks. That machine was ENIAC, the Electronic Numerical Integrator and Computer, and its construction absorbed nearly 2 years of engineering effort from a team led by John Mauchly and J. Presper Eckert. But building the physical machine solved only half the problem. Someone still had to figure out how to translate a firing table calculation, an equation involving multiple variables and iterative steps, into a sequence of physical operations the machine's vacuum tubes and switches could actually execute. Nobody had done this before. There was no software industry, no established methodology, no textbook describing how to program a general-purpose electronic computer, because ENIAC was effectively the first machine of its kind ever built. The Army selected 6 women from the pool of human computers to solve this problem: Kathleen McNulty, Jean Bartik, Betty Holberton, Marlin Meltzer, Ruth Teitelbaum, and Frances Spence. Their formal job title remained close to what it had always been: computing work, categorized administratively at a level well beneath the engineers who had physically built the machine. The distinction mattered enormously in terms of recognition and pay, and it mattered almost not at all in terms of what the job actually demanded. What these 6 women were being asked to do had no precedent anywhere in the world. They had to look at ENIAC's physical architecture, 40 separate panels of switches, cables, and function tables, and figure out how to make its various components execute a coordinated sequence of operations that would solve a real mathematical problem. There was no software to install because software as a concept barely existed yet. Programming ENIAC meant physically connecting cables between different units of the machine and setting thousands of mechanical switches to specific positions, each configuration representing a different step in a calculation. A single program could require rerouting hundreds of cables across the machine's panels, and if even one connection was wrong, the calculation would fail in ways that gave almost no indication of where the error actually occurred. The women had to develop, essentially from first principles, the logical thinking that would later become the foundation of computer science, breaking a mathematical process down into discrete steps a machine could execute then translating each step into a physical configuration of switches and cables that had never been tried before. Access to the machine itself was severely limited during the earliest stages of the project. Wartime security classifications restricted who could view ENIAC's complete logical design, and the women were often working from incomplete technical documentation, forced to study block diagrams and reason out how the machine's separate units, its accumulators, its multiplier, its function tables, actually communicated with each other. They spent hours physically crawling into and around the machine itself, tracing individual wires by hand to understand what each connection actually did, building an internal, working model of ENIAC's logic that existed nowhere in written form because nobody had written it down yet. In effect, they were reverse engineering the very machine they were also learning to program simultaneously. The technical challenge deepened once actual programming began. ENIAC had no stored memory for instructions in the way modern computers do. Every program had to be physically wired into the machine's structure before each run, meaning the women were not writing code in any modern sense, but building a temporary, purpose-specific circuit configuration for each calculation, then tearing it down and rebuilding an entirely different configuration for the next one. Debugging meant testing each section of the wiring independently, isolating which of thousands of possible connections was producing an incorrect result, often by manually stepping the machine through its calculation one pulse at a time, while watching indicator lights to trace exactly where the logic broke down. This was intellectually demanding work that required simultaneously understanding electrical engineering, advanced mathematics, and a form of logical systems thinking that had no established name yet. By the time ENIAC was ready for its formal public demonstration in February 1946, the 6 women had successfully programmed the machine to calculate a ballistic trajectory faster than the shell itself would take to travel the same distance, a feat that stunned even the engineers who had built the hardware. The demonstration ran flawlessly. What the audience did not see, and what history nearly failed to record, was that the women who had made the calculation possible were never introduced, never named in press coverage of the event, and were not included in the formal photographs distributed afterward showing ENIAC in operation. The machine received credit as an engineering triumph. The programming that made it functional was treated as invisible labor, assumed by observers to be a mechanical extension of the hardware itself, rather than the product of original intellectual work performed by specific, identifiable people. For decades afterward, the women's contributions were misattributed or simply omitted from the historical record of computing's founding moments. Photographs from the ENIAC unveiling that showed the women standing beside the machine were later captioned in some archives as unnamed models or support staff, an error that persisted in institutional records until historians and researchers began actively investigating the discrepancy decades later, cross-referencing personnel records and technical logs to reconstruct who had actually written the machine's first programs. What emerged from that research was unambiguous. These were not clerical assistants running calculations someone else had designed. They had independently developed the logical framework for programming a general-purpose computer, working without a language, without prior methodology, and in several cases, without full access to the machine they were being asked to master. The broader significance of what the 6 women accomplished extends well past ENIAC itself. The programming techniques and debugging methodologies they developed through direct hands-on necessity became foundational to the emerging discipline of computer science as it formalized over the following decade. Concepts they worked out through trial and error, breaking complex processes into discrete executable steps, systematically isolating errors within a larger system, and thinking about a machine's operations as a sequence of logical states became core principles taught in computer science programs that did not yet exist when these women were solving the same problems from scratch on a factory floor of vacuum tubes and cable panels. What makes their story resist easy summary is the same contradiction that ran through their entire wartime service. The United States Army needed people capable of inventing an entirely new intellectual discipline under time pressure during an active war with no existing body of knowledge to draw from, and it found those people among women whose official classification never rose above clerical support. The mismatch between the technical brilliance the work actually required and the institutional label attached to the people performing it was not a bureaucratic oversight. It reflected an assumption widely held at the time that calculation itself, no matter how sophisticated, was inherently secretarial work when performed by women, regardless of what that calculation actually involved or what original thinking it demanded. History eventually corrected part of this record. Kathleen McNulty, Jean Bartik, Betty Holberton, Marlon Meltzer, Ruth Teitelbaum, and Frances Spence were formally recognized decades later by the computing industry they had helped create, inducted into recognition programs and historical archives that finally identified them by name, rather than treating them as an unnamed extension of the hardware they had brought to life. But the recognition arrived only after historians went looking specifically for what institutional memory had allowed to disappear, a reminder that invisibility in the historical record is rarely accidental and rarely self-correcting. The machine that could calculate a shell's trajectory faster than the shell could fly did not run itself. It ran because 6 women classified as clerks spent months inventing the discipline that would eventually be called computer programming, wiring intellect directly into a room full of vacuum tubes because no other method existed yet, and no one had told them it couldn't be done by people who weren't supposed to be capable of doing it. Every dusty page still hides a name history forgot to remember. Follow Iron Women Archives, and let's keep prying those pages open, one forgotten woman at a time.